All right, so we've been working with the tree diagrams, and I just want to do one more example here with the tree diagram. This one's a little bit different in regards to the information they provide us. We got to be thoughtful once we start filling in probabilities. So suppose there are two stoplights between your home and school. On the many times you have taken this route, you have determined that 70% of the time you are stopped on the first light, and 40% of the time you are stopped on both lights. If you are not stopped on the first light, there's a 50% chance you are stopped on the second light. What is the probability that you make it to school without having to stop at a stoplight? Okay, so creating our tree diagram here, we've got two events. We got the event of stopping at the first light or not, and then stopping at the second light or not. So I'm going to set up, just say stoplight 1 and stoplight 2. Okay, we could either stop or not stop, right? Those are our options. Is that okay with everybody? If we stop at the first light, then when we get to the second light, we could stop or not stop, right? Okay, so these tree diagrams are very similar. I mean, this is very similar to yesterday's when we had, male, female, and then we got two options. The next one stems off as being male, female, okay? But this one here, we have to construct a tree diagram because of these probabilities and to organize these probabilities that they provide us. So I'm just gonna go through line by line and try to determine where these probabilities should go. It says, as you've taken this route, you've determined that 70% of the time you are stopped on the first light. 70% of the time you're stopped on the first light. So along this branch, remember I'm putting my probabilities on these branches, so 0.7 should go there. Does that make sense? So by giving me that and using my complement events, we should know what probability goes down here. 0.3. All right, so continuing through, it says in 40% of the time, you're stopped on both lights. 40% of the time, you're stopped on both lights. Now, these lights, if I get stopped on the first one, that is independent of whether I get stopped on the second one. Does that make sense? So when they ask me, what is the probability? I want to know what is the probability on that branch right there. Just the probability of getting stopped on the second one, given that I was stopped on the first one. Think about this. The probability of going and stopping on light 1 and stopping on light 2, isn't that equal to the probability, because they're independent events, of probability of stoplight 1 or stopping at stoplight 1 and the probability of stopping at light 2? That kind of makes sense? They're saying that this should be 40%. Do you know the probability of stopping at stoplight 1? Should be 0.7, right? We don't know the probability of stopping at stoplight 2. That's what we're trying to figure out. So how do I figure out this probability then for stopping at stoplight 2? Divide, okay? So that probability of stoplight 2, that is, or stopping at stoplight 2, that is my variable in this case. So I'm gonna take 0.4 and divide it by 0.7. I'm just gonna round this to 2 decimal places. That's actually a 57% chance, okay? So the probability for not stopping at this second light would be the complement to that, right? So 0.43. Is everybody okay with that procedure on doing that? And then if we go through the last one, it says if you are not stopped on the first light, if you are not stopped on the first light, so we're already through here, there's a 50% chance that you are stopped on the second light. So if I'm going this route, not stopped, there's a 50% chance that I'm going to take this route here. So 0.5 should go there, and then 0.5 should go there. Is that okay with everybody? And now the overall question, once we got our table set up, the overall question is, what is the probability that you make it to school without having to stop at a stoplight? So that route of not stopping on a stoplight would be that pathway, right? That makes sense? So what do I do with those two probabilities to determine that pathway? Multiply them together, okay? So 0.3 times 0.5 is 0.15, right? Okay, so 15% chance that we are going to make a school with no stoplights. Is that all right? Yes?
Does this picture say you, I'm in love with you and I always have that, like, I've been in love with you forever?
That's, yes, exactly what that says. All right, key term, Venn diagrams. You guys have questions on tree diagrams, first of all? Like, is this pretty straightforward? Okay.
Yeah.
Venn diagrams, I think, is going to be also pretty straightforward. There's two ways that we can illustrate a Venn diagram. We can actually put the actual objects in the Venn diagram, which is what I want to kind of work with you doing here on this example. And then an alternative way, and I will demonstrate it, is just putting the total number of objects. Okay, so kind of explain that as we build this. So I'm gonna actually, you don't have to do this, but I'm gonna make a copy of this and make a comparison of the different ways that you might see a Venn diagram kind of created. First way says, basically what we're gonna do is our sample space is gonna be the numbers 1 through 30, okay? And we're going to have some subsets of that list of numbers. And they're gonna be your prime numbers, your multiples of 3, and your factors of 30. Okay, so my sample space, I don't wanna write all these out, but your sample space is going to be 1, 2, 3, 4, 5, 6, 7, all the way up to 30. Is that okay? So when we deal with prime numbers, the prime numbers that we're going to choose are the prime numbers that are in this sample space. So what is the first prime number that shows up in this sample space? 2. Okay, so by definition, prime numbers are numbers that are bigger than 1. Okay, so 1 cannot be prime, and that are divisible by themselves and 1 only. Those are the only factors. So as we do this, 2 should be 1, 3 should be 1, 5, 7, 11, 13, 17, 19, 23, 29. We miss any? That should be all. Okay. Is that something we can do? All right. Now, multiples of 3 would be, essentially counting by 3, right? So 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. And then factors of 30. How do I find factors? So if 1 is a factor, then what else is a factor? 30. So you found that by dividing 30 by 1, right? If 2 is a factor, what else is a factor? 15. If 3 is 10, 5, 6, right? So those should be my factors of 30. Is that okay? All right, so now when we build our Venn diagram, I think it makes sense to kind of analyze what, I like to go to the innermost intersection. That's the intersection, that yellow right there would be intersection of all 3 categories, right? Okay. So remember what intersection means. Intersection means that it has to be in every single list. okay? So we're the intersection of, and it's even in S, okay? Because S is the entire sample space, so it's the entire square or rectangle. That little yellow region is the intersection of P, of M, of F, and of S, okay? So what number or numbers are in all three of these lists? And 3 should be the only one, right? Okay. So what I'm going to do, I'm going to put 3 there. Okay. And this is one way of creating our Venn diagram, is to actually write in the Venn diagram what the exact objects are. Okay. Next thing I want to do is I'm going to expand this a little bit, and I'm going to focus on now everything that's yellow. Well, everything that would be yellow there would be the intersection of P and M, right? Okay, so P and M, so what intersects P and M? We've got 3, which is already in there, I'm just going to go through 5 and see if 5 is checked in the M, is 7 in M, is 11 in M, so I'm going to keep doing that all the way through. Are any of these other values of P also in M? No, so I'm going to leave this empty, okay? I'm then going to come over here and try to focus on that intersection, so P and F. So 2 is in P, is that in F? Yep. 3 obviously was. 5 is. Is 7 in both? Nope. Is 11 in both? Nope. 13. So that was all of them, right? So 2, 3, and 5. We've already got 3 in there, so I'll put 2 and I'll put 5. That's okay? And I'm going to do the same thing then right here. Okay, so that's the intersection of M and F. So green M. So we've got 3. 3 is already in there. 6 is in both. 15's in both. 30's in both, right? So I'm going to go down here and we'll write in 6, 15, and 30. All right, so there's still other values that we're missing. So the values that we're missing, so I'm just going to look at just M. Okay, we have already shown that 3 is in M, 6 is in there, 15 is in there, and 30 is in there, right? So then in this other portion, now we already said that there shouldn't be anything in there. We already said that that should be left vacant. So then 9 needs to be here. So does 12, 18, 21, 24, and 27. Those are the values that are in M that are nowhere else. Is that okay? And now we do the same thing for F. So if I'm looking at F, we have already said that 2 is in there, 5 is in there, 3 is in there, 6, 15, and 30. So 1 and 10 need to be there. Is that okay? All right. You can now look up here at the prime values and go through and say, okay, well, 3, 2, and 5 are already in. So now 7, 11, 13, 17, 19, 23, and 29. Okay, you might think, yeah, we're done. But we're not, because there are values in 1 through 30 in our sample space that have not shown up at all here, right? For instance, the number 4. 4 is not anywhere here, right? Okay. 5 is here, 6, 7, 8 is not in there. 9 is, 10 is, 11 is, 12 is, 13, 14. 14 didn't make it. 16 didn't make it. 18 is. 19 is. 20. Did 20 make it? Nope. 20. 21. 23 is a prime. 24, 25. 25 didn't make it, right? 26, 27, 28. So those would be the values that are in my sample space, but are not prime, are not a multiple, or are not a factor.
Yeah, 26 is in there.
Did I miss 26?
Yeah.
Well, thank you.
You're welcome.
So you can see where, obviously that's easier to figure out these if I would have listed this entire sample space a little bit more explicitly. Another way of doing this is just identifying the amount of objects that are in. So would you guys agree in this innermost, there's only one object in there? In this little bubble here, there's only 2 objects. In this little bubble, there's only 3. There are none there. 7 up here. 2 there. And we got 6 here. And then 4, 8, 9, that way. So you can see it written either way. Okay, but to actually come up with the one that we just did, we actually have to know the one on the left, what that looks like. Okay, so that's something to think about as you go through certain questions, certain scenarios. They might ask you to do either one of these. Okay, but now if the question is, if we reach into, let's say we put these numbers on a index card. Okay. One number on each index card and put them in a box. And we reach in and say, what's the probability that you pick out a card that is a multiple of 30 or a factor of 30? Okay. Or sorry, multiple of 3. Okay. Or a factor of 30. That would be the probability that it's a multiple of 3. What does OR mean? Add. Plus the probability of being a factor. Now we got to ask ourselves, are these going to be mutually exclusive or not? Okay, if I don't even answer that question, I'm just going to say that this formula needs to have the removal of being a multiple of 3 and a factor, okay, of 30. So that's our general formula. And now all I've got to do is say, okay, well, what's the probability of being a multiple of 3? So all I do is I look at the circle that is identified as multiples. So it's that circle right there. How many objects are in that circle? If we look at it that way, there's 6 plus 3 plus 1, right? There's 10. If we look at it over here this way, these are the specific 10. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. Okay? So probability of getting a multiple of 3 is 10 out of 30. Okay? Hopefully that maybe makes sense based on the number being 30 and the multiple of 3. Now, the probability of being a factor. Being a factor of 30. How many things are highlighted there blue then. So it'd be 2, 4, 7, 8, right? In the Venn diagram, the benefit of the Venn diagram is to recognize whether events are mutually exclusive or not. And here we see that these events are not mutually exclusive. They can occur at the same time, and they occur at the same time how many times? 4. So there are, between the numbers 1 and 30, there are 4 values that are multiples of 3 and factors of 30. Okay? So those 4 got counted here in this green 10 out of 30. They got counted 4 times here in this 8 out of 30. And we got to remove that 1. So this will give me 14 out of 30. Okay? Now, that's the formula. But if I just do the highlighting, count that number once, count that number once, count that number once, that number once, and that number once, and I add those together, what do I get? What's 6 plus 3 plus 1 plus 2 plus 2? It's 14, isn't it? Okay? And we had a total number of 30 things to choose from. Okay? So we can ask, there are so many different types of questions that we can ask. I can ask, what is the probability that it is a factor given that it is a multiple of 3? Okay, so remember what that means. That means the probability of a factor and a multiple divided then by the probability that it was a multiple, right? Okay, and we can figure out those individual things. Okay, and these would be independent events, so we can multiply these, the probability of F times the probability of M. But here's my question. Does it make sense that if it says given M, everything else is of no concern to me? Because now I'm narrowing my focus on just M, right? How many of those that are in M are factors that show up in the F bubble? Just 4, right? Only these 4 show up in the F bubble. And now because I'm only focusing on the yellow bubble M, which had 10 things in it, it's 4 out of 10. So probability that we have a number between 1 and 30 is randomly chosen, and that I pick it out, and I'm holding it, I tell you, hey, it's a multiple of 3. Then you have a 40% chance, if you know what your multiples of 3 are, you have a 40% chance of guessing the number on my card without seeing it. Does that make sense? Okay. So looking at Venn diagrams, hopefully, allows you to understand the sample space a little bit better than looking at just this information here and saying, okay, given that information right there, given those sets, what's the probability that I have a multiple given that it's a factor? Okay, that would be very hard to decipher from just looking at the data in lists like that. Okay, if we can put it into a visual Venn diagram, it makes things so much easier to work with. Okay, I'll do another example down here. This is the one we did with the last class. Sometimes when just getting practice in your homework tonight, I'm not sure if there's context to the question or not, but they might just say, here is a Venn diagram, answer the following questions, and we've got what they say, N of S. So that N refers to the number, or the cardinal number of the set, which basically means how many things are in that set. That's the notation we use. So it's 120. Okay, so there's 120 things in here. If we add them all up, we would find that obviously, just real quick, I'll do this. We got 8 plus 2 is 10, 17, plus 38, 17 plus 38 plus then the 15. So we've only got 70 things listed here. So that means out here, there's 50 things. Does that make sense? 50 objects out there. Now, I don't know what these things refer to. They might be, patients in a medical study that maybe have experienced maybe like side effects from a medication. Okay, and those side effects are identified as F, G, and H. Okay, Only 2 people, if we think about that, only 2 people would have experienced all 3 side effects. Does that make sense? 50 people would have experienced no side effects. But if it asks you what's the probability of F, okay, this is a situation where we don't know what the individual people in F are, but we know, like we don't know their names, right? But we know that there is how many of them? 27 out of the original 120 in the sample space. So if I asked in this study, let's say F was maybe a side effect of being fatigued. 27 out of the 120 people felt fatigued in this study. I don't know what the individual people were, okay, what their names were, but we know there were 27. Does that kind of make sense? Okay. Okay, so G or H. G or H, we'd be looking at all of G, okay, and all of H. And looking at it visually, just to make sure that when you do this, that number there and that number there, how many times should they be counted? Only once. So we're going to be looking at what, 34, 36. If I add that one in, so that's going to be 50, 65, 72. 72 out of 120 are in G or H. Okay. Is that something we can do? Which obviously that I think visually is a little bit easier than if you remember the formula for G or H. That formula is probability of G plus probability of H minus the probability of G and H. Okay, so that can be figured out or found by taking all of G. So there's 17, 27, 51 things in G out of 120, plus then H, so there's 21, 23, 38 items in H. Okay, if I add those together, obviously that gives me what? 89, and it's not the 72 that I'm looking for because I counted these 17, those were the ones that were in G and H. And now if I do that with a formula, does it give me the 72 out of 120? But my hope is that you see the Venn diagram, the structure of that sample space is so much easier. If you have it in front of you, you can count things, add things up. It's quicker than using the formulas. What about F and G? How many are in F and G? 12. Okay, F and G would be that region there. So we're looking at 12 out of 120. And it says, are F and G independent? Okay, you guys remember what it means to be independent. Probability of F and G, okay, to be independent, if we go back to right here, these were the rules for being independent. The probability of A given B is the same thing as probability of A. Probability of B given A is the same thing as probability B. If we can prove one of these 3 things, probability A and B is equal to probability A times just probability B, if we can do those 3 things, or one of those 3 things, then the events are independent. Okay, so let's do F and G. Is that the same thing as the probability of F times the probability of G? Well, we know F and G. We just did that. That was 12 out of 120, right? Is that the same thing as the probability of F? How many things are in F? Well, that was 27 out of 120, right? Times then probability of G. Well, how many things are in G? 34, 36, 51. Are those 2 things equivalent? Is that there the same as that there? If I take 27 times 51, do I get 12? If I take 120 times 120, do I get 120? No, so these are unequal, aren't they? Okay, so are these independent? No, these are dependent events. You can do the same thing by finding, probability of F given G. Does that equal the probability of F? And you can do the same thing, reversing it. Probability of G given F, is that the same thing as the probability of G? So doing that, then remember what given means. So that means I'm going to just focus on G, right? Just do one of these. Just focus right on G, because that's what the given means. Okay, so how many things are in G? If we add these up, we got 34, 36, 51, right? So my denominator for F given G is going to be 51. And if it's in F, knowing that I'm looking at G, the only ones that are in F are those 12, right? Does that equal the same thing as the probability of F? Well, the probability of F, we said, was 27 out of 120. If those were equal, these events would be independent. But because they're unequal, those are different, the events are dependent. Does that kind of make sense? Okay, so that's how you can decide. I don't know, and like I said, I don't know the scenario here, but we could argue if the scenario was that F stood for being fatigued from this medication we took, G maybe was that we're groggy, and H maybe we got headaches. Okay, we could say because of that knowledge of the information that we got in that data, we know that the events are dependent, meaning that maybe fatigue depended on whether I was groggy, or getting a headache maybe was dependent on being fatigued. Does that make sense? Or fatigue dependent on having a headache. There's a dependency somewhere within them. That doesn't tell me the exact dependency. No, maybe I have to do further analysis of that. But those are unequal, so they are not independent. Does that kind of make sense? Is that pretty straightforward? Yeah. All right, so what I don't like about this text, and I share this with you guys in